Hi everyone, I'm Mr. Fullerton, and today I'd like to talk to you about magnets and magnetic fields. Our goals are going to be to explain how magnetism is caused by moving electrical charges, to describe the magnetic poles and interactions between magnets, and finally to draw magnetic field lines. Now, what is magnetism? Magnetism is a force caused by moving charges. Permanent magnets are caused by the electrons, the charges in the atoms, spinning in roughly the same direction. Not all of them, but a majority of them spinning in the same direction gives you a net magnetic field in that object. Now there's really a lot more complexity to it than that, but that's a first pass explanation of how magnetism works in a permanent magnet. In a non-magnet, the spin of the electrons is much more random, so all the little individual magnetic fields from those moving charges cancel out. In an electrical magnet or an electromagnet, the electric current provides the moving charges to create the magnetic field. So, what type of field is present near a moving electric charge? An electric field, a magnetic field, both, or neither? Well, because it's a moving charges create magnetic fields. We must have a magnetic field, and since it is an electric charge, you also have an electric field. So the correct answer must be 1, both. You have an electric field because you have an electric charge, and because it's moving, you get the magnetic field. Now, magnets are polarized, meaning every magnet has a north and a south. If you happen to have a magnet that has a north and a south, and you cut it in two, you actually get two magnets that each have a new north and south. You can't ever cut a magnet in two and have just a north and just a south. The north end of a magnet points toward the Earth's geographic north pole, and the south end of a magnet points toward the Earth's geographic south pole. Now, again, there are no magnetic monopoles. You can never have a north without a south. Materials can be classified as magnets, non-magnets, or magnetic attractables. Magnets create magnetic fields. Magnetic attractables are things like a paperclip, for example, that you can pick up with either end of a magnet, a north or a south, but it's not a magnet in its own right. And non-magnets are things like a block of wood. If you put a magnet near a block of wood, you really can't pick it up. So, north and south poles can attract magnetic attractables, but you can't repel from a magnetic attractable. The other thing you need to know about magnetic forces is the closer the objects are, the stronger the magnetic force. The further apart they are, the weaker the magnetic force. So, another sample problem. We have here in the diagram a 0.5 kilogram bar magnet and a 0.7 kilogram bar magnet with a distance of 0.2 meters between their centers. Which statement describes the forces between the bar magnets? And it asks us about gravity and the magnetic force. Well, right away we know gravity can only attract. So a gravitational force that repulsive doesn't work, so that eliminates 1 and 2. Now, because the closest poles are the norths, those will have the strongest forces, and those are like poles, so they will repel. So the gravitational force is attractive, gravity always attracts, and the magnetic force is repulsive. Answer number 3. Another problem, a student is given 2 pieces of iron and told to determine if one or both of the pieces are magnets. First, the student touches an end of one piece to one end of the other, and the 2 pieces of iron attract. That tells you that you must have at least one magnet, and the other one is either a magnet or a magnetic attractable. Then the student reverses one of the pieces and again touches the ends together, and they attract again. Well, if they attract from both ends, that means one must be a magnet, the other must be a magnetic attractable. If they were both magnets, when you flipped one, you would get a repulsive force. So what you know is that at least one of the pieces is a magnet, and the other is a magnetic attractable. All right. Here we have 2 ring magnets placed on a pencil. Magnet A remains suspended above B as shown. Which statement describes the gravitational force and the magnetic force acting on A due to B? Well, again, the gravitational force is always attractive, so we can get rid of anything that has gravitational force as repulsive. Because A is being suspended above B, that must mean that B and A are repelling each other in order to hold A up above B. So we know the gravitational force is attractive. The magnetic force must be repulsive. Answer number 1. Now, magnetic field lines or magnetic flux lines show the direction the north pole of a magnet would tend to point if placed in the field. And this is very similar to what we did with electric field lines or gravitational field lines. Magnetic field lines are drawn as closed loops, and the magnetic field is strongest in areas of the greatest density of magnetic field lines. So down here on the bottom left, we have a picture of a bar magnet with the north and the south. The magnetic field lines always run outside the magnet from north to the south. Inside the magnet, they run from south to north to make that closed loop. But outside the magnet, those field lines run north to south. So in this problem, the diagram shows the lines of magnetic force between two north magnetic poles. At which point in the magnetic field is the magnetic field strength greatest? And our choices are A, B, C, or D with those little dots. Well, the magnetic field strength is greatest in areas of the most field lines, the greatest flux density we call that. And I see the greatest density of lines over here by B. So B must be our answer. It has the greatest magnetic field strength because it is located in the highest density of magnetic field lines. Hopefully this gets you started with magnets and magnetic fields. If you're looking for more help, need more information, want to go more in depth, check out aplusphysics.com. Thanks for your time and make it a terrific day.